It's the age-old question. What is dark matter? Like, is it some kind of particle that doesn't interact with regular matter except for gravity? Is it that we just don't understand gravity at the largest scales? If it is a particle, what kind of particle is it? And astronomers have proposed a lot of different kinds of particles, very massive particles, very light particles. And there's one class of particles called axions that have sort of more behavior like light, but also matter. And astronomers have been looking for evidence for this. So my guest today is Dr. Amruth Alfred, who is a PhD student at the University of Hong Kong. Actually, he just got his doctorate, so I guess post-doc at University of Hong Kong. We talk about the observations that he studied in a gravitational lens that hints that maybe the axion is the right explanation for dark matter. And then we also just talk a lot about gravitational lenses because I am so fascinated by these and how they work as natural telescope lenses. You've given me a lot of questions and I was able to pass a lot of those questions along to Amruth. So enjoy this interview with Dr. Amruth Alfred. And I gotta say, that is the coolest recording setup I have ever had talking to an astrophysicist. This is the this is the first time someone comes prepared with a condenser microphone, a nice set of headsets. This is the best. I'm really honored.
Thank you. Okay, now I do some streaming on my own time, so I had to upgrade, slowly, get the decent equipment at least.
Yeah. I think that's my new rule. I'm only going to talk to scientists who are also video game streamers and professional esports
that probably
players.
probably raises the bar.
Yeah.
I mean, you're going to get good audio and video.
Yeah, exactly. You've already gone through all of the hassle of getting your setup done, and then we can talk about the science. So that's it. No more of the people always give me a hard time. They're like, "Oh, the audio quality of your guests is so mediocre." I'm like, "Oh, but they were so interesting." But all right, so let's talk about gravitational lenses. Let's start with the big news and the reason that I reached out. So you and your team put out a paper, picked up by some pretty big places. What was the discovery that you are proposing in your paper?
Well, so conventionally, dark matter, people treat it as, it's made of massive particles. And that's sort of the standard paradigm. And then there's this alternative model called wave dark matter, where the dark matter is just made of very light particles. That's really the main difference. And then, there's a lot of other models because the standard paradigm ran into a couple of issues, both in particle physics and astrophysics. Right? There's been decades of searches and really billions of dollars of funding looking for these massive particles. People call them WIMPs. For weakly interacting massive particles, and we haven't really found any. So there's a lot of motivation to consider other ideas, and
so sorry, just to interrupt. So like this, what is the difference? I mean, I think we can kind of wrap our heads around the idea of a bunch of particles that are not interacting with regular matter. I mean, that's already pretty hard. But what is this idea of like wave-based dark matter?
Right. Well, it's just because the particle is so light, right? And then I'm sure you've heard about, wave particle duality, right? Everything is actually a wave as well, or a particle. And then this wave behavior becomes stronger the lighter you get. So very light particles are going to have very large wavelengths. We call this the de Broglie wavelength after Louis de Broglie. And so because these the candidate particle for wave dark matter is so light, they're ultra light particles, their wavelength is so large that on astrophysical scales, they kind of behave like waves. They exhibit wave-like properties, kind of like, interference patterns and stuff like that, like waves on a beach.
So theoretically, you could throw streams of dark matter particles and they would interfere through interference patterns like photons.
Right. Yeah. So on large scales like galaxies and galaxy clusters, it's kind of like ripples in a pond. They interact with each other. They have these interference patterns. And then, every interference pattern, whenever that happens, there's constructive, destructive interference.
Right.
So you get all these funky behavior, which you wouldn't get with massive particles. They just wouldn't show this kind of thing.
But to all other purposes, it still behaves the same as that it is cold, that it doesn't, has a small cross section, doesn't interact with itself or regular matter through anything but gravity.
Yeah, no, that's so that's important. And there's still people who work on hot dark matter, warm dark matter, the three classes. And it's just that astrophysical observations prefer dark matter to be cold. It's not to say that all of it's cold. Some of it might be warm, some and even less hot maybe. But looking at the large scale structure of the universe, and then you compare it with simulations, what it tells you is that probably dark matter needs to be cold. And slowly moving. And then, so, wave dark matter and then massive particle dark matter, they're still cold. This is important. You need to, there's like primary astrophysical observations that you need to reproduce if you want to consider that model, seriously. And then two of these main ones, there's a couple, but the two main ones are, you need to be able to reproduce the large scale structure of the universe, right? So all the structure we see, like the cosmic web. The second is you need to be able to reproduce the cosmic microwave background, the CMB. And then those two, you need in any kind of cosmological model. And then wave dark matter, as well as the, standard dark matter, they both do this.
Right. Okay.
Yeah.
And so what is the observation then that you were making?
Well, we didn't actually make the observations ourselves. We used data from a previous team that did it, from previous work. So this has never been done before, really, where people test dark matter models with gravitational lensing when it comes to lensing of quasars. And quasars are just distant bright galaxies, right? And historically, for almost 2 decades now, astronomy and lensing has had this problem called lensing anomalies, where when you look at lensed images of very distant galaxies or quasars, and then you try to reproduce the brightnesses of those images, what we find is that standard dark matter models can't reproduce these brightnesses more often than not.
Interesting. So in this case, like you've got a galaxy cluster foreground, and then you've got some quasar in the background, and the galaxy cluster is acting as a lens for the quasar.
Right. You actually have a galaxy as the lens typically.
Okay.
Galaxy
Sure.
cluster.
Galaxy as a lens. Yeah. And so the brightness that you're getting of this lensed quasar doesn't match up with what the predictions should be.
Right.
And is that because it's like you need more mass in the lensed galaxy or less mass?
We don't know. You can't tell. You can't tell. Like it doesn't tell you. And then people have tried invoking different explanations to, try and circumvent this problem, and then they've kept running into a wall where none of these explanations seem to, sometimes these explanations help resolve the problem, but more often than not, they don't.
It's dust, obviously, but.
Well, yeah, sure, it's dust.
It's always dust. Like it's always dust,
right? Yeah. It's, dust, full stop. Yeah. People try adding in these subhalos, which are sort of like mini galaxies, and then the standard cold dark matter paradigm predicts these kinds of invisible galaxies. Well, invisible halos of dark matter. Is just, I don't know why people use the word halos in the field. Halos, if you told a stranger halo, it's like a ring on your head, right? Like angels have halos. But when astronomers use halo, it's just a spherical cloud of dark matter. So they say dark matter halo, it's just, a blob of dark matter. It's very misleading. I hope people listening, I'm saying this because people listening are like, why is there a ring of dark matter? But it's just it's a cloud, a spherical cloud. And then, the standard theory simulations predict many of these smaller halos, sort of like baby halos around the parent halo. And we don't see these in observations. It's one of the problems called the missing satellite problem, which is one of the things that plagues the standard paradigm. Around our Milky Way, around our galaxy, simulations predict about more than hundreds of satellite galaxies, but we only see a few tens. So there's a large discrepancy there. And people tried to use these baby halos, subhalos, to see whether that could help resolve these lensing anomalies. And sometimes it can, but then sometimes it can't. Yeah.
And I know it is tricky because in some cases, if you do have like a baby halo and it has primarily dark matter and no stars, it's really hard to see it.
Yeah.
Yeah. And I don't know if you saw some Chinese scientists found a dark matter satellite galaxy to the Milky Way a couple of months ago, relatively close. So they're out there. They do exist.
Right.
But not at the quantity that you would be expecting.
Yeah. And I'll probably get a lot of flack for this from the standard cold dark matter people, but
yeah, they're not listening. Don't worry about it.
Yeah, okay, they're not going to be listening, right? It's the cool people listening.
Yeah.
No, because it is a topic of debate. I'm not saying that it's guaranteed 100%, but it's definitely a topic of strong debate, and especially in the past, it was much more severe, but. Nowadays, some people say that, okay, it's not really a problem. It's just that our simulations suck. And then if we have better simulations, then this isn't really a problem. And sure, it might be the case. But it's just definitely a topic of hot debate, because there's other issues as well, apart from this missing satellite thing.
So you looked at these lensed quasars, and what were you hoping to see?
Well, so, I did tell you this, but all this time people were finding brightness anomalies because you couldn't reproduce the brightnesses. But more recent observations, which with much higher resolution, with radio telescopes, it's called VLBI, very long baseline interferometry. When you use these, the resolution you get is orders of magnitudes higher than the Hubble Space Telescope, which is, like the holy grail for astronomers. Well, now the JWST in infrared. And then what we found is, there's these brightness and position anomalies, that what people found. And then we were like, look, wave dark matter, it has this wave-like behavior, right? And then one of the defining characteristics is that it produces this kind of interference pattern, which leaves behind a lot of structure in the mass. So it's not like smoothly distributed, but there's a lot of blobs of mass that are more dense and less dense than the average density. So you might want to picture it like, I don't know, when waves crash on the beach, like the froth that forms, It's sort of like that. It's like a lot of structure going on. And then this is a very unique prediction. It's not the same thing as adding in these baby halos, because the baby halos are just adding in mass, right? But this wave dark matter, it's going to have negative fluctuations as well.
And so is this like structure in the galaxy itself because of the effect of the dark matter, or is this purely something that you're seeing in the lens? Like, is it structure actually there around the galaxy?
Yeah. So the first time, we found this out was in 2014. That was the first time that's full simulations of wave dark matter were done, also by one of our collaborators. And it turns out every galaxy has this kind of structure. It has this wave-like behavior, taking over, and this kind of interference pattern, leaving behind this very rich structure. And then it happens in galaxy clusters as well. So basically every dark matter halo.
Right. Yeah. Okay. And so when you look at a gravitational lens, where is this? I think about things like, for example, astronomers are able to see exoplanets around other stars just by using gravitational microlensing.
Yeah.
It's such a sensitive technique.
Yeah.
And is that sort of what's doing the heavy lifting here? Is the lens itself?
Well, yeah, the lens is what's important here, definitely, because what happens to the lensed images lets us probe what's going on in the lens. And that's why we can infer something about the dark matter distribution. In this case, it's not microlensing because it's strongly lensed images, so it's strong lensing. So you especially in the radio, you even see resolved images. So you don't just see blobs, but the particular object we're looking at, it's it's an interesting object. It's a quasar, so it has a central core of the galaxy, which is imaged only in optical with the Hubble Space Telescope. But then it has two radio jets on either side, kind of, going out of the center, and then that's imaged only in radio. And then this jet, it has a lot of structure. It's actually incredible when you see it, because there's only a handful of these radio lenses. You could literally count them on like one hand. So it's very rare. It's very rare. So that's something we try to emphasize in our work. We're like, look, you need, if you can get radio imaging of lenses, you're going to be able to do incredible stuff with it. So this thing is really, really interesting, a central core and then a radio jet coming out of it. And then all of those provide very rich constraints that you could never really do before in lens modeling.
And so if this is true and what you're seeing is correct, what are the implications for cosmology?
Well, what this would tell us is that probably it's time to take, the candidate particle for wave dark matter is called axions. Mm-hmm. It's just the technical term. Fun fact, most people don't know why it's called axions. Do you know why it's called axions?
No, I don't.
An axion, yeah. Well, so the person who proposed this was Frank Wilczek. So he's the Nobel Prize laureate in 2006. And then the axion, it wasn't just proposed as a candidate for dark matter. It was proposed for solving other problems in physics, in theoretical physics as well. And then he said, look, it cleans up a few problems in physics. And then he was in his kitchen, and then there's this detergent called Axion. I don't know if you've ever seen it. It's like a cleaning detergent. It's a company. Yeah. Right? And then he saw it and he said, look, I'm just going to name it Axion. So that's where the name comes from.
That's amazing.
Physicists are, sometimes they have questionable names, but sometimes they're pretty funny.
I think it's better than a backronym. So I think it's all right, So, right. And so like a lot of the people who are watching this or listening to this, they're familiar with the term axion, but essentially what you're saying is that of all of the proposed explanations for dark matter, if you are seeing these structures in the lens are correct, then the axion is the most likely candidate for dark matter.
Right.
Or something like it.
Or something like it. That's what this particular these anomalies tell us. And that's something, it's very interesting because you could never really do that before. But so we're very careful to, say that lens models can always be more perfect. Like they can always be better. We're not really capturing the lens, realistically, because we're limited by the models we have and how best we can represent a galaxy. So there's still some additional work that needs to be done, which is what we're hoping to do in research, in some of the research that we have planned. We want to try to capture the galaxy as best as possible in simulations. But assuming all of that wouldn't make a big difference, then if axions were the true particle, for dark matter, then that's going to have cosmological implications as well, because there's a lot of variation. There's a lot of different predictions that wave dark matter, axionic dark matter would do as opposed to massive particle dark matter.
So for people who, they're familiar with the name, what is the underlying astrophysical process that's believed to create axions?
The astrophysical process
or the particle physics. Like, how do you get axions?
So there's multiple hypotheses. I shouldn't use the word theories. There's multiple hypotheses on how they're formed, and then there's the axions actually span a wide range of mass, and then what we're looking at is ultralight axions. But there's also axions that are more heavy, much more heavier, like orders of magnitude heavier, and they all have different purposes in particle physics. And then there's a lot of processes like symmetry breaking in physics, and the particular axion that we're looking at, it's postulated in string theory. I don't like using the word string theory because it's not a theory. I don't know why people use that word. String hypothesis. Yeah, it should be. You know, if you're doing science, you wouldn't call it a theory, I think. So you know, it's predicted through all these a variety of mechanisms. There's a whole host of them, and you know, to be honest with you, I couldn't tell you the details. It gets incredibly complicated, and I couldn't tell you the details on how that works.
But I know there are people attempting to detect them directly. There's even like an axion detector set up at CERN.
Right. Yeah, there's direct detection experiments, the same as how people were looking for WIMPs. But the searches started a bit late. But I think, you know, some of the earliest searches were in the late 90s as well. But there's such a large parameter space to be explored that, you know, because WIMPs have had now lots of decades to be searched for, and presumably you'd think maybe axions would need you'd need some time to explore out the parameter space. But there are direct detection experiments. I actually went to this conference in Santander in Spain last week, where it was just about dark matter. There were still tons of people, you know, doing planning projects and looking, you know, direct detection experiments or even indirect detection experiments. There's a lot of people working on stuff like that. Maybe not on axions. Most of the people were looking still for WIMPs or heavier particles, but there were a few. So it's still not, you know, that popular. So we got a lot of pushback when we actually sent this paper. In. So the paradigm still has a strong grasp on most scientists, I guess.
Has the pushback helped you strengthen your position?
Well, you know, what my supervisor
it gives you pause, right? Like you got all these people going, you're wrong.
Yeah.
And you say, explain how, and then they do. Right. And then you go, am I wrong?
Yeah, right. No, that's a good question, because that's what science is all about, right? You want to, you know, check out all the questions. And then unfortunately, a lot of the pushback we got was not really on the science we did. You know, for example, when we had to send this paper in and through the referee process, it was very painful, because from one of the referees, most of the comments we got were on the introduction of the paper. So it wasn't on the science or the methodology or the results. They just had issues with how we were phrasing things in the introduction. But that was, you know, what you do in an introduction of the paper is just a literature review, right? You don't actually say other things. So it's just people are willing to, they're not willing to accept that the current paradigm has problems that can't be easily resolved. Sure, you know, you can pull in a lot of magic ingredients if you want, but there's problems that, you know, and I'm not saying that wave dark matter is right, you know, massive particle dark matter is wrong, right? Because you can never say that, and when we emphasize that in the paper as well. But a lot of the pushback is kind of because people have locked in, they've kind of put all their money into that idea, and they don't want to consider the alternative idea. So whenever we get, you know, sometimes we get questions from people about our paper and what the issues could be, and then there's good questions like that, like, you know, we need to do a more analysis in the future, like a better modeling of the galaxy, stuff like that. Sure, you know, that's part of science. But a lot of the pushback, yeah, it's quite sad to see.
Why are these radio lenses so rare? I mean, I know that there are dozens of Einstein rings and other really great gravitational lenses seen by Hubble. Why are the radio equivalents so hard to find?
Well, they're so hard to find because we don't really know where to look. Like, you'd have to first know that the lensed quasar you're looking at has jets in the radio, which you wouldn't know beforehand. And well, radio observations are expensive, I guess. You need to do, you know, lots of it, and it's difficult to do. You know, when I started research, I started off with as an undergrad, I started off handling data from the VLA, the Very Large Array, and then radio. Oh my God, dealing with radio data is crazy. I don't know if you've have some experience. You've heard someone talk about it. It's incredible. The amount of respect I have.
Yeah, I mean, my perception as as an outsider, as someone reporting on this, is that in the beginning, even like when I started as a journalist, like you would see pictures from the Hubble Space Telescope, and there were these beautiful wide field views of the sky. Yeah. You would see stuff from, and like a telescope, you can point it at the sky, take a picture, and now you've got a gigapixel image that you can look for things that are interesting in there. But with a radio telescope, you've got this tiny, you've got like 4 pixels, 10 pixels, 100 pixels at the most that you're scanning across the sky. Degree, not even degree, arc second by arc second, and you're slowly building. And it's only been recently, like when you think about some of the telescopes like Meerkat, you're seeing larger structures because the thing can just gather more pixels of the sky at the same time. And now suddenly you're seeing these incredible filament structures at the center of the Milky Way. And it gives you this glimpse that radio telescopes are about to start taking pictures of the sky that look like photographs in the way that Hubble and JWST and all these do, because they finally can gather a wide enough field of view, which is really tricky, right? Because a radio telescope, you just point at one little point in the sky, you go, strength of the signal, okay, move over. Is there a signal here? Okay, move over, right? Like it's a totally different world. And so I can see how finding these things, there isn't going to be a Vera Rubin of radio telescopes for a long time.
Yeah, the next exciting one is the square kilometer array.
Yeah,
that would be the big one. That's going to start finding thousands of lenses, we think. But just the precision with the resolution that you can reach with interferometric techniques. That's the key part. And then radio lets you do that in radio. When you use interferometry, the resolution that you can get is just incredible. You just can't get it with non-interferometric
So what if you turned the Event Horizon Telescope on this lens?
I have no idea. That the resolution of, I think the Event Horizon Telescope is orders of magnitude even better than what you could do with than what has been done. I don't know. You'd start seeing crazy stuff probably.
Yes, like yes, please. Host of new things. Yes. But you think, do you think, make a prediction, right? Like if you convinced, and obviously, after this interview goes live and the steering committee of the Event Horizon Telescope, now that they've imaged all of the black holes that they can, need something else to use this collaboration for, and they're going to be like, okay, fine.
Right.
Amruth wants this. Let's do it. What would you predict that you would see in the quasar lens if the wave dark matter is more likely?
Right. Well, barring any technical difficulties, I don't know whether the engineers at the Event Horizon would be like, no way. I don't know about that part. But if we could get an image, you would be seeing really any astrophysical object. It would have never been done before in history. It would be an unprecedented level of resolution. You'd manage to resolve structures, in the radio jet to such a fine precision. And if wave dark matter was what the galaxy was made of, the lensing galaxy, these images would have variations, both in brightness and position, and the kind of variations you would see, it would be determined by the wavelength of the particle. So it wouldn't just be, you can constrain the mass of the axion with these things, which we can also do kind of. It's just not, within an order of magnitude, a few orders of magnitude. But what you could do here is, you'd be seeing effects that, we haven't even predicted it, because we don't do simulations for sources that small. Because you just never would be able to see it in the observation.
But an astrophysical jet coming from a quasar fits the bill. I mean, like it gets more and more point sources. You get closer and closer to the source of the jet, and to image a gravitational lens, you're already getting the benefit of however many orders of magnitude from the magnification of the foreground galaxy. That'd be bonkers.
Yeah, I mean that would be amazing. That would be
Yeah.
amazing. You'd be seeing a whole host of new things. You know, apart from all these really odd things happening to the lensed images, who knows what, you know, you might be seeing some new phenomenon as well. The images would be jiggling about. You know, they'd be shifting in position and brightness, and then you'd be able to really capture all of these. And wow, the lens model that you could make with that kind of data. You could rule out a lot of stuff with that kind of data.
Yeah, and I guess that's the question, right? It's like if you don't
Right.
see anything interesting,
Right.
then
You'd be able to rule out wave dark matter.
Yeah.
And that would be awesome too, because, you know, that's one of the good things that we're proud of when we were doing research, and we're happy of. It's very falsifiable, because, well, you know, nowadays there's a lot of models going about in all of science, really, where there's a ton of free parameters, and then you tune the knobs, and then you fit the data. And I don't know if you call that science. I don't. Right.
But if you were able to wipe out an entire field of research with one observation, you'd be okay. You'd be able to sleep at night.
And I'd be happy.
Right? Like, I think this. I mean, this is the thing that I think people like. If you could just like go, oh, you know what, dark matter doesn't exist at all.
Yeah.
With some series of observations, you'd be fine with that.
Yeah, I'd be so happy. I'd be so happy because I think the fun part is knowing things like that. You know, where you can be like, it's this whole thing. It's not that. That makes it way more fun. Even if I was invested in one of these ideas, but I try to, you know, stay away, have an open kind of mind, so that I don't get down into one idea, because I really think that's like the killer. Especially if you want to have like if you want to be a scientist, I don't know, you can't just do this getting into one bandwagon. And I feel like it's a trap that you tend to fall into if you want to focus on your career as a scientist.
What do you think causes that trap?
I think it's part of the career path. If you want to get, you know, I just finished my PhD like last month. If you want to get, even if you want to get a good PhD, or you want to get a good postdoc position, right? And then after a few postdocs, you probably want to apply for a faculty position. You need to be probably an expert in one field nowadays. Back then, maybe you could, you know, maybe if you're crazy enough, you could be an expert in multiple fields. But you need to be an expert in one field, and then, you know, you get your faculty job, you become a known person in the field, and then now some 20-year-old kid comes and tells you, no, you know, look what you've been doing for a few decades is wrong, right? And I think it's a very human thing to be a bit defensive about this. And so people are not willing to kind of accept and then let go and be like, look, the kid's right, you know? And I think it's part of like a human, I don't know, a defensive thing that ticks off. And if you don't jump into one of the bandwagons, then it's going to be harder to progress your career. I think that's what I've heard from other people.
Yeah, but at the same time, you get these, you know, I think scientists love to hear these stories where after working for decades in, you know, against the resistance, someone was able to prove that gut bacteria leads to ulcers, or that plate tectonics is correct, or, you know, there's all of these ideas that in hindsight are accepted by the scientific community, and it was just a difficult haul to get to convince
you know, that's like Einstein's relativity. It wasn't really accepted. You know, he never won a Nobel Prize for it. Yeah. Now, if you ask someone on the road, they'll be like, "Yeah, he should have got 5 Nobel Prizes."
Right.
He didn't. You know, for each one of his papers in the Annus Mirabilis, he should have got a Nobel Prize for each one of those. It's the pillars of modern physics.
Yeah.
The guy did relativity and quantum physics, and then, you know, people were like, "No, relativity is wrong." Even after, you know, they looked at the solar eclipse and saw the lensing. I mean, there was a lot of proof. So yeah, you got to fight through the resistance sometimes, and it's a skill, I guess. It's a skill, because people are going to be, you know, looking down on your work, or just constantly saying, "No, you're wrong. No, you're wrong." You got to be able to handle that and to keep going, I guess.
But does that, like, you know, when people are telling you that you're wrong, and that makes you sharpen your own skills, ideally.
Yeah.
That you're like,
Right.
you think I'm wrong. I'm going to prove that I'm right. I'm going to go back and I'm going to double check. I'm going to fix every single mistake that you identified and do even better science.
Yeah.
So do you think like just on average, like I can totally get why 20-year-old coming into this would be like, I'm right. Like, why won't you people listen to me? Right.
Yeah.
And they're like, well, come on. We've been doing this for a long time. And we have a certain amount of wisdom, and you might be right, but you're probably not.
Right.
So let's just start with you're probably not right.
Yeah.
And the scientific method is encouraging you to take that as well and to push through, even though you might be wrong or are probably wrong.
Right. Right. No, yeah, that's definitely the attitude you need to have as well. You know, whenever you get criticism, the first thing you want to do is to ask yourself and then go through those questions and see if that's going to help you make better work. So definitely you need that attitude. Yeah. Because if you don't, then you're not going to, if you end up being wrong, then you're not going to learn from it if you don't have that attitude. So that's important. There's a lot of good criticism out there. And then there's some which is like, there's no foundation to it. Those ones you got to kind of, so this is the attitude we needed actually to get this paper published. We even with all the very harsh comments from the one of the referees, we were like, okay, we're gonna try our best to address the comments. We didn't like argue back or something like that. We were like, we'll do our best to address the comments, and then the editor was like, look, it's good.
Yeah. Yeah, and it was in Nature Astronomy, just so people understand. Like your paper was published in Nature Astronomy, which is a pretty good paper. Right.
Well, I think people got excited about it because we were like, look, if we use this wave dark matter model, we can resolve these lensing anomalies that have plagued the field for decades. It might be, able to solve anomalies.
I want to talk about gravitational lenses because I'm a huge fan of these. I mean, we don't, if they're mostly made of dark matter, then we don't know what they are, but we can use them as a telescope, which is crazy to me.
Yeah.
What are some of the like apart from your work that you just did, what are the sort of like the best uses of gravitational lenses, do you think?
Honestly, gravitational lenses are pretty much cosmic telescopes, right? That's the phrase we like to use. And really it's sort of like a magnifying glass. The way we're using gravitational lensing in our paper, and people who study dark matter, is kind of the opposite of what you normally do with lensing, where lensing actually, what it does is it lets you see something you could never see if it wasn't lensed. It wouldn't be magnified in the sky like a magnifying glass. And then what that lets you do is study the object, that's far away, right? But what we're doing with dark matter is we're studying the object that's doing the lensing.
Right. So it's like you're looking through a telescope and you're using the image to figure out whether or not your glass is good or not.
Exactly. Right. That's a good analogy. You're trying to figure out what the mirror of your telescope is. Exactly. But lensing does a lot of cool stuff. With respect to technosignatures, one of the ideas that I had, which I'm working on, is trying to find out, trying to look for signatures of wormholes using gravitational lensing. So wormholes have a very distinct signal. They leave behind a distinct signature when they lens something. So it would be different to black holes or galaxies or stars or planets. There is a distinct signature. And then if you look for this signature in light curves of microlensing, for example, you'd be able to see this. And there hasn't been any search for it. There's a few papers that predict what it should look like.
Yeah, I remember. I know we reported on that a couple of years ago that there was some proposals that if there are wormholes, then you would see them through gravitational lensing.
Right. And then the Event Horizon Telescope, in their paper, they also looked at, what if what we're looking at is not a black hole but a wormhole. So they do consider different exotic objects. That's what it's called. But with lensing, what you can exactly like what we're talking about, you can study the lens or you can study the source. It's kind of like a two-way thing, and that's already incredible, because in astronomy usually you just end up studying one object. The lensing
And what
lets
is
you
the
do both.
power of the lens? Like, in terms of magnification?
It really depends. It really varies. And then some of these galaxy lenses, the magnification can be hundreds in some areas, in these special regions called the critical curve. That's sort of where the image, a circular image would form. That's what we call an Einstein ring. It can be hundreds, a few tens on average maybe. But if you were talking about galaxy clusters, then you can go into thousands.
Wow.
And then depending on the size of the object, there are some studies that look at backgrounds, stars being lensed, and the magnifications can reach tens of thousands, 50,000. Imagine, something being magnified by 50,000 times. That's insane. That would let you see so far back.
Yeah, like
right?
Imagine the Hubble Space Telescope, and then 50,000 more of them bolted together.
Right.
That is a big telescope.
And I forgot to mention this, but lensing is a particularly powerful probe for dark matter, as well as for looking at things, because the light just traces the mass distribution. You don't have to worry as much about all these interactions and complex things going on in a galaxy, which other people have to worry about. If you're talking about, for example, the missing satellite, some people say that there's all sorts of, outflows and interactions between dark matter and normal matter. And then if you don't take those into account, then you can't really solve the missing satellite problem. But in lensing, there aren't a lot of outs. You can't make a lot of excuses, basically. And that makes it fun, because you can't just tweak the knobs and then explain away something.
Right.
So it's a very clean test bed.
Like the lens shows what it shows.
Right. It shows what it shows, so you can't mess around too much.
I mean, back to that idea of like exoplanets with gravitational microlensing. Like it's so, and I think it's the same thing, right? That you are using a foreground star to image a background star, but it is the planets orbiting the foreground star that cause variations as the lens is going past, and it's so sensitive that you see these warpings of the brightening of the background star that tells you, there's a planet, it has half the mass of Mercury. Oh, second planet, twice the mass of Jupiter. Oh, third planet, it's a terrestrial planet, and then now we never get to look at the gravitational microlens ever again. Like I hope we were recording, because it never comes back.
Yeah. Right. Yeah. Yeah.
And it's that sensitive. Like in many cases, the smallest planets ever seen are in these microlensing. The lensing is so fragile, and yet it's so sensitive, right?
Yeah. Yeah. These little peaks, the equipment we have, the technology that humanity has right now, it's sensitive enough that you can see these peaks being made, and that is incredible. It's not something it's not a conventional way of observing things.
What does it take to reconstruct the image that you're seeing from a gravitational lens? Like when you see, say, an Einstein ring, and it is this blur all the way around the lens, can you turn that back into a picture of a galaxy, or can you just get, are you looking through the smear of a galaxy and you can make some inferences from that?
No, you're right. You can turn it back into the image of a galaxy. And then in the field, people call this the source reconstruction. You're just reconstructing the source galaxy. But to do this, you need a good lens model. And by lens model, it just means the mass distribution of the lensing galaxy. Because you need to know how to map back the Einstein ring image into the original source, right? So you can do that. And, we kind of have to do that for some people doing lens modeling do that. There's quite a lot of degeneracy involved, because it depends on your lens model. So you never really know if what you're, reconstructing is how the true galaxy looks.
And
but
so
you can definitely do it.
If you had a perfect model of the lens, from like really good observations,
Right.
then you
Right.
could
Right.
perfectly create the object that's being lensed.
Yeah.
And vice versa, if you knew exactly what the object that was being lensed was, you could create the perfect lens model.
Exactly. Yeah. Right. And then, you know, that's one of the incredible things you can do. So some of the work that, you know, some different work we're doing, we're trying to do this kind of source reconstruction to see what the background galaxy looks like. And you can do a lot of science with that. Even if you don't know if your lens model is the perfect one, you can do a lot of science with that. You know, you might be able to distinguish between a spiral galaxy and an elliptical galaxy. You might be able to, you will know the size, or at least an upper limit on the size. And then, you know, you can do a lot of science with that stuff.
Do you think that we will get to the point where you can like see a picture of a spiral galaxy? It looks recognizably like a spiral galaxy, as opposed to, you know, it has enough signatures that tells you that it's probably a spiral galaxy and not an elliptical galaxy. Like, do you think, can we make better lens models?
I mean, that would be so cool. I to my knowledge, I don't think anyone's reconstructed a spiral galaxy.
Yeah.
I think, you know, we definitely should be able to do it. I think, I don't know when, you know, maybe within the decade.
What would it take to make the best possible lens model? Is it a bigger Hubble Space Telescope to make observations on the lensing galaxy?
What you would need is a very nice observation of the lensing galaxy. And then usually this gets harder and harder as you go to higher, as you go further away, as you observe things that are further away, because the lensed images start to outshine the lensing galaxy. So it kind of disappears. So that might not even, you know, the telescope might not even matter too much at that point. But if you could manage to image something a bit closer, and then, yeah, you know, if you had a bigger telescope that really, and then you observe in different wavelengths. So, you know, multi-wavelength observations, that's what you need. And many lenses don't really have it. You know, some of these, like I said, a handful have radio and optical. But, you know, if you could do it in a wider spectrum and you really saw all the structure that's going on, then you'd be able to make an incredible lens model. At least the data is available.
Yeah. I'm going to channel some questions that I've gotten from my viewers for you for a second here.
Yeah.
Have we ever seen a double lens?
By double lens, does that mean there's two background galaxies being lensed by the same foreground galaxy?
No, that
So
there's like
two different...
one lens magnifying another lens, magnifying something behind that.
Oh, like a line and a line and a line?
Yeah.
To my knowledge, no.
No, okay. Yeah, I didn't think so either. I searched through the literature. I couldn't find any examples where you had. Yeah. I mean, it would be phenomenal, right? Because then you would get 50,000 times 50,000, or 100 times 100.
So this is a very interesting question, because even if you saw one, you might not know that it's a double lens. You get it? Because you don't know. One thing in lensing is you don't know what the true brightness of the object behind is, because it's being magnified by a certain amount, right? And if you don't have lens models have a problem where the magnification, you can change it. It depends, unless you break it with some specific observations. So you might actually be seeing a double lens, but you might actually not know that this image is being double lensed.
So you could see an object and you go, that might be a spiral galaxy, or it might be the stadium of an alien civilization. We can't tell.
Right. Yeah. So I feel like you might be able to help distinguish with spectroscopic observations. So you need like emission lines and absorption lines so that you could determine. But that's something interesting. I don't think I've never come across a double lens situation. Maybe there's one in literature, but it's interesting because
right.
So I want to say that data there might be data which has double lenses, but we just don't know how to look for them.
All right. Well, I'll dig up the person who asked me that question, and then you can add them as a contributor on your paper when you get your Nobel Prize. And then the other one is, how dynamic are these like cosmologically distant gravitational lenses. Like we know the micro lenses change over the course of, say, a day as the stars line up perfectly and you get this flare and then it fades away. How dynamic are the ones that are at these cosmological distances? Do you see changes over time?
Right. So then, that's something interesting that's kind of started to become a hot topic when you talk about galaxy cluster lenses, which is what, the JWST, the first image it released, is a galaxy cluster with all these incredible lensed images and structures.
The 2-mass one.
And then, right. Yeah. And when we look at these galaxy clusters with better and better observations and, more observations, so you kind of can make like a video, right, over like a decade. And then you realize these things light up like a Christmas tree. They're pretty much blinking. The lensed image, a large lensed image of a galaxy, of a background galaxy, it has little, it blinks in certain places along the image. So that's people think that's because of microlensing. That's one explanation. But there's also, it could be millilensing, which is just lensing by slightly more massive objects like these subhalos or the density fluctuations predicted in wave dark matter. So these things, they're lighting up, right? And the time scales, these can be months. And like you said, the microlensing can be a few days or weeks. But if it's millilensing, it could be, months or years. And then sometimes that it could be even longer, sometimes decades. It really depends on the configuration.
And we know
the lens system.
Like when I know that astronomers look at, say, supermassive black holes and they see the accretion disks around those black holes, and even though they can be hundreds of millions of light years away, you're seeing active processes brightening, dimming on the order of years, months, or even years in the disk around one of these supermassive black holes. And so you could be seeing that, but lensed. Yeah. Or you're actually seeing these kind of wobbles and warps as the two objects are passing one another from our perspective.
Yeah, you're incredible. You should. Are you an astronomer?
No. It's just a journalist for 25 years. That's all.
Then you should just hop on and into our research group, because you just hit it on the head. Because that's what people do when they measure the Hubble constant. For cosmology, when they infer the Hubble constant using lensed quasars, this is what they do. They track they stare at a quasar, at a lensed quasar. So there's 4 images, and then they look at the variations in brightnesses of these images, which happens because of the variability in the accretion disk, like you said, which we think. And there's a time delay, because that when the light reaches you depends on the mass distribution, and then so there's a delay between all 4 images don't brighten up at the same time. There's a delay, and then this delay is what lets you infer the Hubble constant. So it's important that that this delay is because of the variability in the accretion disk, and not because there's something in the lensing galaxy kind of amplifying it.
And there was an amazing piece of research where people are watching this supernova pop off in a lensed galaxy, and they're seeing it happen with various delays over the course of multiple years. And so you can even predict, like, on this day we should see the supernova appear at this portion of the image. Yeah. And we can watch the entire cycle. Like, normally you can't see supernova. Yeah. You don't know the progenitor of a supernova until after it's happened, and now it's too late. Mm-hmm. But now, through this lens, they'll be like, watch here, and you'll see it, the whole cycle. Right.
Yeah, it's incredible. So one of the people on this paper is one of our collaborators as well. And I don't know if you're talking about the same one, but there's one where they predict the image to appear in 2037 or something like that. Yeah. Yeah, that one. So it's incredible. It's so cool.
Just by
let's hope people remember. What if people forget? It's like it's like 14 years later.
Well, the computers, everyone's going to be gone. This will be after post singularity. The computers will remember. That'd be fun.
Okay. Yeah, I'm happy with that.
Yeah, that sounds awesome. Well, if people want to track your work, what's the best place to do that?
Well, I'm on Twitter, and I post about our stuff, about our research. That would really be the best way.
Okay.
I'm not too active on anything really. Or archive. That's the website where people post.
Or Nature Astronomy.
Oh well, maybe in a decade.
Yeah. What is the other and what's the game you mainly play?
Oh, I play a lot, and I play Dota too.
Okay.
I don't know if you know Dota. It's like League of Legends, but
yeah.
Dota,
So what's your main? What's your favorite main on Dota 2?
My favorite what?
What's your favorite hero on Dota 2 that you play?
Hero? Juggernaut.
You play mainly Juggernaut. Okay, all right.
Juggernaut, yeah. But I play a lot of others. But I also play Valorant. I don't know if you know it. It's by Riot.
Yep.
So these are all competitive multiplayer games. So I
prefer support personally, but
right.
That's okay.
Yeah. You mean reals for it?
No, support. Like Crystal Maiden.
You mean
right?
Support?
Yeah.
Oh, you play? Mm-hmm. That's incredible.
Yeah.
We should play sometime.
Hell no.
Are you
kidding me? No way.
Crystal Maiden and Juggernaut. That's like the best combo. I know.
Right? Yeah. No way. It would be. Yeah. Sure. On the same team. Yeah. But no, thank you. Well, it was a pleasure to talk to you. I really appreciate it.
The pleasure was mine.
It was great to talk both about sort of your work, but also just how great gravitational lenses are. I'm a huge fan.
Yeah.
And hopefully so many new discoveries will be made from this, including wormholes. Let me know when that happens.
That would be my dream. I'd be happy to take one and then just get out of here.
Here you go. Nobel Prizes all around. Yeah. And then away you go. We'll see you on the other side of the universe. All right. Good luck.
Thank you. Thank you so much, Fraser.
We'll talk to you later.
For giving this opportunity. Yeah.
You can get even more space news in my weekly email newsletter. I send it out every Friday to more than 60,000 people. I write every word. There are no ads, and it's absolutely free. Subscribe at university.com/newsletter. You can also subscribe to the Universe Today podcast. There you can find an audio version of all of our news, interviews, and Q&As, as well as exclusive content. Subscribe at universitoday.com/podcast or search for Universe Today on Apple Podcasts, Spotify, or wherever you get your podcasts. A huge thanks to everyone who supports us on Patreon and helps us stay independent and keeps ads at a bare minimum. Thanks to all the interplanetary researchers, the interstellar adventurers, and the galaxy wanderers. And a special thanks to Just Paul Davis, Vlad Shipolin, Jay Dennis, David Gilton, Maud So, George, Jeremy Mattern, Jordan Young, Tim Whalen, Dave Verabioff, Andrew M. Gross, and Josh Schultz, who support us at the Master of the Universe level. All your support means the universe to us.